Good afternoon, everyone. My name is Alexis Ruth, and I'm leading a team of data engineers and data scientists at Vertices Intelligence, where we are focusing on building a graph of all US businesses, which is used by our software as a service cloud to offer predictive marketing capabilities. I've had the opportunity to architect and implement our complete data pipeline, and we have been using a lot of GraphX lately. So in this presentation, I will give an overview on how we use Spark technologies to build a comprehensive and accurate graph of all US businesses, created from data coming from dozens of sources. In particular, I will zoom in into how we use GraphX to build our business graph and link businesses together. Just as a show of hands, how many of you have heard about Vertices Intelligence already? Great. I think you'll get a good sense about what we do after that presentation. The agenda is the following. I am first going to introduce Vertices Intelligence. Then I will lay the foundation of the talk by introducing objectives and terminology. This will take a bit of time, so please be patient, but the remaining of the presentation should be worthwhile. The bulk of the presentation will focus on our graph data pipeline, and I will give an overview and a good amount of details on how we use GraphX there. I will wrap up with lesson learned and Q&As, so please hold off on questions during the presentations. Vertices' main offering is predictive marketing software. It is designed for marketers to discover new markets, acquire new customers, and measure success for these new customers. Our software as a service solution empowers marketers with both software and data. Building a business graph is necessary for us as our customer data isn't typically very comprehensive, nor always accurate. And our solution goes beyond lead scoring. So we have to basically build a graph, comprehensive graph, and accurate for all the US businesses that are used through our predictive segments. We achieve this by taking a data science and data engineering approach, and I will illustrate that during the rest of my talk. Just a little bit more background information about Vertices. It was created over 6 years ago. We have 125 people in 2 offices, San Francisco and Austin. The majority of our staff is headquartered in San Francisco, in Financial District. And we have received a significant amount of funding for some of the top VCs, including Peter Thiel or Salesforce. We have many customers across vertical areas like finance or retail, for instance. You can see a few listed here. And again, one of our core differentiators is the way we use data science and data engineering to offer the best possible predictive marketing platform. As our business graph is used by all our customers, it has to be both comprehensive across all the industries and accurate. As our customers use our software to create marketing campaigns, such as email campaigns, sales campaigns, or social campaigns. So as such, we are building our graph from records coming from dozens of sources, comprising hundreds of data points, such as business name or addresses, emails, phone numbers, websites, employee information, demographics, financial data, technologies used within the business, news about the company, and a lot more. Building a graph allows us to answer complex connected questions, such as finding employees, and employees like engineering executive, for instance, working at a given company and focusing on a given area, like big data or security. Or news, be able to find all the news related to a particular marketing segment, such as funding announcements or mergers and acquisitions. Or intent, showing the companies that have an intent of buying my particular product, or specific employees like engineering manager looking for a given product like security, for instance. Or organizations, be able to show all the locations of a given company along with the employees. And you can see that each of these queries will involve multiple types of data and their relationships. So using a graph for us is a natural way to model that data. I'm now going to define some terminology. Pay close attention as this concept and symbols that I will introduce will be used for the remaining of the presentation. A business represents a company or organization, such as Blue Bottle, which for those who don't know is an upscale coffee chain. I am representing it as a dark disk with a bold border. A location represents a business at a particular address, such as Blue Bottle at Simpson Street in San Francisco, which is actually next to our headquarters. I am representing that as a light disk with a light border. Attributes represent information bits about a business or location, such as an address, a website, a phone number, an industry category, and so forth. I am representing them with small geometrical shapes. In addition, we have a number of other data types, such as employees, intent, news, technology, and so on, which are represented here by a square with a letter inside. At a high level, our graph data pipeline can be broken down into 4 steps: data acquisition, data preparation, clustering, and construction. Data acquisition, in that step, we crawl or license data from dozens of sources, including billions of records and tens of billions of data points. We retain this information over time as we use historical data to build some of the machine learning models. At the output of data acquisition, we have many different types of records which might represent or model the same information in different ways, such as, for instance, employees or revenues. For that stage of the pipeline, we use Spark and Python, while for the remaining of the pipeline, we use Scala. Also, we use Databricks Cloud along the way to be able to do things like exploration, reporting, or testing of our pipeline. The next step is to prepare the data, which includes standardizing the data so that every data type is represented in the same way, such as a standardized address, for instance, website or revenues. We also have to validate the data to get rid of incorrect data. And lastly, we have to normalize the data so it looks the same across records. As an example, we can see raw records on the left across sources, and to the right, a view where we have data which has been normalized, such as, for instance, a single view for employees. The following step for us is to group clusters based on similar attributes, including address, name of the business, and a variety of other dimensions, such as website, phone number, and so on. To the left, we can see the normalized records used as input, and to the right, cluster of records grouped by address and business similarity. There we use GraphX in addition to Spark and Scala, along with in-house libraries to do things, for instance, like name matching, working on syntax and semantic level, given a lot of what we do is really matching records together. The last step of the construction breaks into 2 sub-steps. First, we have to construct the locations, as defined previously, and then we have to construct the businesses, linking the locations together and adding additional information. The first sub-step involves filtering bad clusters. We might have issues with some data across sources. And for each cluster, we then have to select the best value or values. For instance, we have to select the best business name across all the names, across all the records in the cluster. And we might have to rank phone numbers based on accuracy by creating a machine learning model that will use data sources along with historical data. And we might need also to impute missing values as well. At that stage of the pipeline, we use a variety of machine learning models using MLlib, such as logistic regression or random forest. The output is a set of locations as defined previously that is a business at a given address. We can see here that each location is represented by a color disk and content attributes per previous definition, which have been resolved. The second sub-step is to construct the business graph. There we link all the locations representing the same business and add new data types that belong to a business versus a location, such as employees, news, or intent. Lastly, at that stage, we can correct or impute some of the fields at the business level. So for instance, correcting the revenues based on location within the group. We can see to the right that we are putting 2 businesses here, the red and dark blue disks, across 3 locations, pink, the green, and the blue disk, that are sharing a news element, the square with the N letter inside. For the remaining of the presentation, I will actually zoom in into that particular step. As we are going to use GraphX, I'm going to provide a short introduction for those not familiar with it already. In the interest of time, I will not go over its architecture or internals, except to mention that like RGGs, the GraphX property graph is immutable, distributed, and fault tolerant. Instead, I am going to focus on GraphX API to demonstrate that it is very approachable and easy to use. Show of hands again, how many of you have used GraphX already? Great, couple. So GraphX, very simply, models a property graph, which is an attributed, multi-directed graph. Multi-directed allows multiple parallel edges or relationships sharing the same source and the same destination vertex. And attributed simply means that the vertices, also called nodes and edges, and the edges as well, can have attributes. This shows a very simple graph that has 3 vertices, a location, a domain, and a phone vertices, and 3 edges or relationships linking those vertices. You can see here that multi-directed is used as we have 2 edges linking location and domain, allowing us to show that 2 sources provide the same website link. Let's now look at how GraphX model that information. The graph can be accessed as an object through the graph class, or as a table of vertices, edges, and triplets. A vertex represents a node, an edge a relationship, and a triplet 2 connected nodes with their relationship. At times, using a triplet can improve performance over using individual nodes and edges. We can also see that vertices and edges store attributes or user-defined objects represented as VD and ED types, as defined previously, as I explained previously with the attributes. In addition to the graph, I'm showing here at the bottom the RDD definitions, which are extending RDD to support additional capabilities like allowing a unique ID for vertices, for fast joins, or partitioning of the edges in blocks. GraphX offers a number of operations which are similar to RDD, which are functional and lazily evaluated. I'm listing here the complete list of operations supported at the graph level and at the vertex and edge RDDs. You can see the list is rather succinct, and it will essentially group into a few areas, including high-level information of the graph, such as the number of vertices or edges, access to collections, such as the vertices, the triplets, or the edges we've defined previously, transformation, like for instance mapping vertices or filtering out, joins, aggregations. I will, during the remainder of the presentation, zoom in into aggregate messages, as it will be used in the pipeline, caching, and some graph algorithm. And there again, I will zoom in into connected components. And there are also a number of operations available through the vertex and edge RDDs. Now that I've laid the foundation for what we do at Reduce and what GraphX provide, I'm going to zoom into the construction of businesses and linkage of locations and explain how we go from locations to the business graph. I will go over the main steps, but clearly there are a lot more details that I will leave uncovered. The first step is for us to generate the location vertices based on the clusters. We start by the clusters produced by the clustering stage of the pipeline and map each cluster to a vertex location, limiting to the attributes which we'll need for linking locations. As such, we can see that the location embed attributes. Our data pipeline figures an optimization for non-large businesses. For this, we have a curated list, including key attributes such as name or website. We map every entry of that list to a vertex business. This allows us to improve performance and accuracy. In this next step, carrying on step 1, we want to link locations and non-businesses if there's a relationship, such as a domain. We start with what we created before and use flat map operation to project attributes inside out. Locations are not keyed by their attributes, and we can see in this simplified example that we have a few relationships between location and businesses. Specifically, the pink place shares the pink attribute with the red business. Let's assume that this type of attribute is a domain, which would be coming from a website or an email. The green and blue locations share a yellow attribute with the dark blue business. We then join based on key attributes. This yields 3 key value pairs representing the relationship we mentioned before. The pink location is linked to the red business, the green location is linked to the dark blue business, and the blue location is also linked to the dark blue business. We can then create edges between location and businesses based on the attribute relationships. And as an output, we get the pink location linked to the red business and both the green and blue locations linked to the dark blue business. In the next step, we want to create a graph of locations with attributes and show how these attributes are actually shared across locations. For the sake of illustration, this example looks like the previous example, but we can assume that we'll have a different set of locations at that point. The intent of the previous step was to focus on non-businesses, while this step will take care of everything else. We start with locations containing attributes representing to the left. We use flat map to get locations keyed by attributes. We then do a group by, which groups locations per attributes. We can see that in this example, blue and green locations share a common attribute. We then create vertices for the attributes and edges based on location to attribute relationships, and we end up with the graph to the right. At this stage, we have created a graph of locations along with the attributes. Graph problems like PageRank or connected component are frequently solved by sending messages from vertices to their neighbors. Aggregate messages provide a functional abstraction for aggregating neighbor information in Spark Graph. Conceptually similar to map and reduces for graph, it consists of two steps or functions defined by the user. First, the send message function accesses information about the edge triplet and passes that information to its source node and or destination node. And then the merge function is used to aggregate these messages at each node. Let's look at an example on a simplified graph. In this example, we can see two locations sharing a domain. We define a send message function that sends the source ID and name to its neighbors, and a merge function which simply aggregates values. Running this on our example yields the sequence of locations for this domain. In this case, the green and the blue locations. We will use that function later. In the previous step, we have linked location of attributes. In that step, we want to link locations together based on shared attributes. To the left, we have the location to attribute graph. We use aggregate messages explained before to reconstruct the keyed attribute to location. In theory, we could have used the computation explained before, but here we want to show that we can perform those operations directly from the graph without having to recompute the graph. The next step for us is to do combinations too. The intent for that is to start comparing each location with every other location in the group to eliminate bad relationships. In this simple example, we only have two locations, hence we have to perform a single comparison, but the number of comparisons will go up as we have more locations. I will actually discuss that in the next slide. We are then applying a filtering function that will compare how similar those two places are. At a minimum, we will apply some sophisticated name matching, but we will use other techniques as well. We assume in that example that the green and blue places are similar, so we create the relationship. And now on combinations too. Complexity is n squared for the worst case scenario. Actually, technically, n squared minus n divided by 2, as we do not have to compare each element with itself, and there's also a symmetry allowing us to subtract n and divide by 2. So in the case of a large chain where all the locations share common attributes, this will create a large number of comparisons, which will be expensive for chains with tens of thousands of locations, as you can see here. So an optimization we do instead for large groups is to find the most common representative and to only compare all locations against that representative location, which leads to n complexity. In that case, approximation is the price to pay for reducing complexity from quadratic to linear for large groups. The connected component algorithm computes the connected component membership of each vertex and return a graph with the vertex value containing the lowest vertex ID in that group. In that particular example, we call connected components on the location graph to the left and end up with two connected groups. In this step, we call connected components on the linked location and create businesses. We start with the locations, we call connected components, and get two connected groups. We then create a business for each connected group. As such, in the example, we create a red business and connect it to the pink location, and create a blue business and connect it to the green and blue locations. Each business is created using values from all locations, and we have to decide what are the best values. At that stage, we have now connected all related locations together to a business. And we have gone from originally creating locations with attributes to linking locations to businesses. A number of performance optimizations are available in GraphX connected components listed here, but connected components is an iterative algorithm, so it's expensive in terms of compute. As such, it is important to perform some steps to improve efficiency, including vertices and edges, should be kept in memory. It is more efficient for us to work with a minimal graph and rejoin the information later. Also, checkpointing can greatly improve performance as it reduces long lineage that may cause part of the graphs and the DAG graphs to be recomputed even when cached. In our case, we do checkpointing before and after connected components, which leads to a significant increase. Now that we have a graph of linked locations and businesses, we can start doing a lot more steps. For the interest of time, I will not detail them here, but they include assigning the headquarter for the given business group, joining additional informations that belong to the business versus individual locations, such as news or employees, doing additional correction or enhancements, such as reuse the websites across all locations, or correct revenues for locations based on the group. We finally eventually get to a full business graph that our cloud platform can use. The business graph is used to match our customer data with ours, augment their data, and provide analytics based on their data. From there, our customer can use our SaaS to search for new businesses or automatically discover new segments through our predictive segments. This is an illustration of what graph looks like for two steps of the pipeline for a small to medium-sized burger chain. The one to the left shows location with selected key attributes, while the one to the right shows location to a business. It is actually funny to plot those businesses as they can have all sorts of shapes and visuals. Does anyone think the one to the right looks like an animal? Maybe a porcupine. That's what my daughter told me when I was preparing the presentation. Here's another visualization for a large retail chain. This one has over tens of thousands of locations. And it's very interesting for us to start exploring those data sets visually. I would like to leave you with some lessons learned. Using a graph is a very intuitive way, a natural way to model relationships. The world is connected and looks like a graph. A graph makes it very easy for us to add new data over time. It also makes it very easy for us to debug data and pipeline through interactive visualizations. Creating a graph is easy. If you really know Spark RDD transform, it's really easy to manipulate, and you only need to learn a few additional constructs, such as some of the one we covered before, mainly aggregate messages or connected components. GraphX scales very well also. For the clustering part of our pipeline, we use over 250 million vertices and over 1 billion edges. Edge coding is as much of an art as a science. We are constantly looking at new ways to improve that through data engineering, heuristics, and machine learnings. And as I mentioned before, connected components is an expensive operation, so optimization matters, as we've discussed earlier. But I hope I'm being able to show you that really using GraphX is very easy from a user standpoint. I will now take Q&As, but before I do, I would like to advertise that not like only other companies here, we are hiring, and I would like to encourage you to check out our openings at radius.com/jobs, or come talk to me afterwards if you're interested. We are looking for data engineers, machine learning engineers, and data scientists to solve complex problems using Spark technologies. Thank you.
Awesome. Well, thanks very much for Alexis for this great presentation. If you have any questions, could you please raise your hand, and I will run over to you and give you the mic.
So when there is new information coming in that you have to add, remove, update, adjust, or what is this, do you handle it in real time, or do you just batch them?
Great question. So currently, the bulk of the processing we are doing is really batch-oriented, although we also do incremental processing. Historically, the company was based on Hadoop up to a year and a half, 2 years ago, so it came from batch processing. And the volume of data we get is rather large and also doesn't come in real time because we license data that we get every week or every other week, and we crawl data ourselves, and we get that constantly. So we don't necessarily have a notion of real time. That being said, because now we move to a graph where instead of having one monolithic business location, we have many different objects modeling the graph. We've been looking at ways to start doing only incremental processing for some of the information, like for instance, the information that is real time, which for us includes primarily news and intent. So for that, we're looking at doing that incrementally, and we can keep the remaining of the graph the same, but incrementally append new types of information.
Hi, from the analytics standpoint, I have two questions. The first one is like, do you have any metrics to evaluate the accuracy of the data you are building?
Yes.
And then also how you validate what you have been doing is right?
Great question. So we have a lot of validations we're doing at various steps of the pipeline. That will include for every step of the pipeline, we actually have QA. So we have a team that's called the reporting team that does help us do a lot of measurements. So to give you an idea, we do significant sampling at every step of the pipeline. That will include, we look at the accuracy of the data source, and for each source, we're going to verify things like, is the business, at the right address with the right name? Does actually the phone number connect? That the associated to the business? Is it the right industry category code? Is it the right websites? And so forth. So we have a pretty large set of metrics basically that we do, and we have external teams doing that on an ongoing basis, both at the data source, at the clustering level, and at output of the build. So we have to measure all the top fields produced by the index because it matters for our customers. So that will include, again, things like name, phone number, industry category, website. So we have about a dozen set of fields that we basically measure. And in addition to that, a lot of what I'm doing, I haven't talked about that, but it's really supervised learning, right? So we're constantly acquiring new data, validating new data. So we have a concept of a vault where we store all our user measurements, and we actually use that constantly to revalidate the data and actually retrain some of the models.
Hi, thank you for your presentation.
Yep.
Can you give more insight about your metrics, like how much data you're consuming? I know that you gave some metrics about the graph, but how long does it take to build the graph? And you gave some pretty good steps which you follow, and how much time
So the number are actually a little bit low on that side. They're a little bit more marketing than actually technical. So we leverage up to 8 billion records right now because we use historical data. So all the data we have, we basically store historically. And we actually use that information because that information is a very good signal for building models. For instance, when you build a model with phone number, it's a great indicator, how long was the phone number valid on record to verify the accuracy of that phone number, because business typically don't change phone numbers, right? Unless maybe they go out of business or move, and even then. So we have very large volume of data from a record standpoint, and then in addition to that, for every record, we will have dozens or hundreds of attributes. So the volume of data is significant. Now for the build, the way we're actually doing it is we're essentially doing it in batch mode, right? So we're essentially reconstructing currently, the entire, process, all at once. Although we uncoupled some of data acquisition and data preparation now, and each step in the pipeline, in effect, is actually separate, right? So we have also the clustering uncoupled from the construction. So if you look, everything end to end on a large, cluster, it takes about 10 to 12 hours. But we have the capability of doing it in phases if we want. But if you want to essentially reconstruct the last index with all the data, that's about how long it takes. Everything is separate right now, so we can actually, for instance, the data acquisition team is constantly, basically acquiring new data, while it's constantly also getting validated on a daily basis now, getting prepared. For instance, we don't want to keep redoing the normalization over and over and over on the same data. So we're only going to renormalize the new data, right? So that, from that standpoint, every step is kind of like uncoupled from the others, right? If you wanted to rerun a new construction by reusing the same data set we had before, then it goes a lot faster. It's only a few hours because you don't have to do all the previous steps in the pipeline.
How do we enforce data governance around this massive hierarchies, affiliations, and relationships between the entities?
Can you elaborate a little bit more about what you mean by data governance?
Meaning like from audit and data security, data privacy perspective, because we have a major challenge in terms of managing from the regulatory and compliance requirements perspective?
So that's the thing. If you're talking about security, I think it's more like a DevOps questions, right? And there's basically a number of things we are doing from that standpoint. I won't necessarily be the best to talk about that right now, but we essentially have SOC certification, so we have to look at how data is basically stored, accessed, and so forth.
Okay, cool. Well, that's it for time's up. So it's time for our break. So I want to thank Alexis for this great presentation.
Thank you.